Alright, today we're going to be estimating pi. And we're going to be estimating it by making a Riemann sum of a quadrant, a quarter of a unit circle, as explained here in the comments. Now our first function is called height x, and this is just circle quadrant function in f of x form. You know, the square root of 1 minus x squared. And the next function, bar xn. In this one, n is the number of subdivisions, I like to call them bars, in a Riemann sum. Each one of which has an area width of 1 over n. And x is the midpoint of one of those bars, the bars we're calculating. So f of x times 1 divided by n. So the height times the width of the bar, basically. Okay. Now SDN, SD is short for estimate, and this is a function where we actually estimate the area of the whole circle quadrant. So n is the number of bars. Sumec is the sum accumulator, initialized to 0 right here. And then we have a for loop. This equation finds the midpoint of each bar. If it's the first bar, it'll be, well, you can calculate in your head and prove it. But that's what that line does. And this one is the sum accumulator, so that each time it calculates the area of another bar, it gets added to the total area until there's no more bars. And that's the final output of this function, SDN. Now error n is so called because it calculates the error. This thing, I didn't want to deal with importing and all that, but this is the figure that Mathmatics will use as its estimate of pi. I made sure there weren't any extra digits before I did this, and there's not. It's just this. But remember, we approximated the area of a circle quadrant, not a circle. And a circle has an area of exactly pi. So 4 times SDN should be about pi. So this basically calculates the percent error, and I wrote this function so that the percent error is not percent, it's just a decimal, because I just like to do math that way. Now, these are all basically helper functions for the coup de grace. This is a function I call pretty, and it's called pretty because it prints out all the information in a pretty format. So SDN, 4 times SDN rounded to 5 decimals, printed out in a sentence, and explain how you found it, calculate the percent error, and you'll see what the output is in a second. Now, last but not least, the last function that I've written for this program is called error-bound n. And the purpose of error-bound n is to find out what's the least number of subdivisions you can use in this Riemann sum that will yield an accurate estimate within 0.001%. That's 1/1000th of 1%. And this Boolean right here is so that it just prints out the number to where the number before it wasn't precise enough, but just this number is. So that number is the winner. So now I've explained all my programs and functions, I'm gonna run them. So you wanted to estimate the area for, let's see, 2, and then 20, and then 2,000, and then 2 million bars, right? So I'm gonna do that right now. Let's do it for 2. Okay, it's about 3.25937, and it's accurate to about 3.75%. And now let's do 20. This estimate for 20 bars. Okay, that's a better estimate. It's about 3.14543. My bad. And the error is about 0.12217%. So that's pretty good. That's about 1/1000th of a percent. So that's a clue for everyone. Anyway, let's try 2000. Okay, even better. And now let's try 2 million. Yep. And the error is not really 0%, but it's so small that it rounds to 0%. So there's a pretty good estimate. Now, you want to know what's the least amount of bars that will make an effective Riemann sum. That's what error bound is for. Now, the thing about this function is that the n in this function isn't quite like the n in the other functions, because it does a Riemann sum, then does another Riemann sum for one bar, then does another, and so on, and it's going to do a lot of Riemann sums in a short amount of time. But it's a finite thing, and finite amount of electricity, finite amount of data, so you have to give it a place to stop. You know, basically a range of numbers to which to scan. So I'm gonna set it as 1000, because that'll probably yield a pretty accurate result. So 494. So if you made a Riemann sum with 494 subdivisions, it will be accurate within 0.001%. So that concludes this video. Thank you, and it's been fun.